So I want to talk to you about the effect of vitamin C, which is a common interferent in the blood, for blood analysis using electrochemical biosensors. So my name is Sheryl Chocron, and I'm from the University of Maryland at the MEMS Sensors and Actuators Laboratory. So let's see. Today, I want to first introduce you to why we use blood analysis for a particular application for sensing clozapine, and a particular modification that we use for amplification of a signal. And then the focus of this talk is how vitamin C interferes with this biosensor. The results, I will compare electrodes, gold electrodes, to gold electrodes modified with biomaterial. So the motivation for sensing clozapine is that clozapine is an antipsychotic used for treatment-resistant schizophrenia, and it is underutilized today because it requires patients who use it required to be monitored frequently, and the monitoring is done for the drug itself in the blood, the drug levels, as well as measurement of the white blood cells. So it's important to know that clozapine is the only treatment for those patients that have schizophrenia that can be treated with the first lines. Our approach has been to devise a more convenient way of constantly monitoring the treatment that uses point-of-care sensors. As you can see here, we have a microfabricated sensor array that is complexed with a multiplexer platform. Currently, it allows us to sense 8 patient samples at once, and this is our first prototype. We use electrochemical sensing because clozapine, as you can see here, can be oxidized by giving up an electron, and it can also be reduced back by gaining an electron. Our microfabricated sensors are modified with the biomaterial chitosan catechol. Chitosan catechol has been developed by our collaborator Gregory Payne at the University of Maryland, and we use it for clozapine for electrochemical signal amplification, as I will show you in a second. So just briefly, electrodes are modified with chitosan by applying a constant current. So we use electricity to deposit this biomaterial, and then we graft a molecule called catechol onto this matrix. And I will show you how catechol plays an important role in sensing. So clozapine makes its way to the electrode surface by diffusion, and it can be oxidized at the surface, and that's how we sense it. Then catechol can actually act as a source of electrons to reduce clozapine back to its original form. And so that allows for clozapine to be sensed again and then reduced back again in a loop that we call redox cycling. So this is an electrochemical oxidation and then reduction loop. And what this does, it allows for each molecule of clozapine to be sensed more than one time. And that's how we get literally electrochemical amplification of the signal. So we've actually observed a ninefold amplification. And this allows us to reach lower limits of detection of clozapine for therapeutic blood monitoring. So I've talked to you about why clozapine, because it's an underutilized antipsychotic that requires frequent monitoring, how we use a biomaterial approach to amplify this signal electrochemically. And now I'm going to shift gears to the topic of today, which is how does vitamin C interfere with our sensor. So there's a challenge in translating from clean buffer solutions to complex blood fluids. You have an additional background that you have to be aware of, and there's potential electrochemical interferences with clozapine. Blood generally contains blood cells, proteins, and other electroactive species, and vitamin C is the most common electrochemical interferent for sensing in blood. It can be oxidized, and it is present at upper limits of 100 micromolar in the blood. So we study how this 100 micromolar vitamin C can interfere with 25 micromolar clozapine concentrations. And this is done in buffer solutions as a proof of concept. So now I'm going to show you first how vitamin C interferes with clozapine in a bare gold electrode. I'm going to call that the unmodified electrode. And then how, comparatively, how it interferes with our modification. So first, to characterize the electrochemical behavior of clozapine and of vitamin C. So now I'm calling vitamin C AA because it's also referred to as ascorbic acid. So to characterize the behavior of these two molecules, we use a 3-electrode cell with a gold sensing electrode connected to a potentiostat. And then we apply a technique called cyclic voltammetry where the potential is ramped, so from positive to negative and then back around. And then we observe the current output. The peaks of the current output give us information about the particular molecule that we're looking at. So in this case, the x-axis is a potential ramp, and then the y-axis is the current subtracted by the phosphate background. So in red, you can see the behavior of clozapine. It has a main oxidation peak at 0.4, and it also has a reduction peak because of its reversibility. And then in black, you see vitamin C, which has an oxidation peak at 0.2. So it's important to see that, that the vitamin C signal is much wider, whereas the clozapine signal is very narrow and it has a very known peak. So we, from seeing this data, we realized that vitamin C could be a potential interference in this region where we want to sense clozapine. So then we decided to sense both of these together and see whether in fact it is a problem. So I'm going to compare that to the individual signals I just showed you. So here in red is clozapine alone with its characteristic oxidation peak. And then this in black is the mixture of clozapine and vitamin C. And we see the features of both, as we expected, of both vitamin C over here and then clozapine at 0.4. But in this case, there's an additional signal that comes from the mixture. So this is a problem in quantifying the amount of clozapine because we're interested in knowing what concentration of clozapine is in a patient's blood. So in fact, in the bare gold electrode system, clozapine does affect the performance of, vitamin C affects the performance of clozapine sensing. So now what's interesting is to compare that behavior with the behavior of these two molecules in the chitosan catechol modified electrodes. So here, the gold sensing electrode has been modified with the film I showed you before, which is chitosan catechol. And as I mentioned, that is used for electrochemical amplification. And I'm going to compare that to the results with the unmodified electrodes. So in this case, in black is the vitamin C. And you can see here that it looks very similar to those with unmodified electrodes. The amplitude with the modification is slightly higher. But then the interesting thing happens with clozapine. Clozapine has the same location, but the amplitude with these modified electrodes has increased 9 times, as I mentioned before. So in this case, the relative behavior of these two molecules is completely different than the relative behavior with the unmodified electrodes. And in this case, we can actually pick out the signal of clozapine over the background of vitamin C. And the reason for this is because clozapine can undergo redox cycling. So each molecule can give electrons more than 1 time. Whereas vitamin C is more unstable, and it can only be oxidized and not undergo redox cycling. So that's not amplified. So the modified system specifically amplifies clozapine, but does not amplify the background vitamin C. So now what happens, this is the true test, what happens when these two things are put together in the same solution? And again, comparing to the mixture with the unmodified bare gold electrodes. So in this case, at the location of clozapine, we don't see a significant shift as we do in the bare electrodes. And then at the location of vitamin C, we do see that there is some signal coming from vitamin C, but it's not affecting our sensor for clozapine as much. So in this case, the effect of vitamin C is alleviated by using this film. And then one last result I want to show you, which is interesting and gave us some new insight, has to do with this location for vitamin C. So why did we see that, even though we see in the mixture that there is some vitamin C peak, why did we not get an interference here? So in fact, vitamin C by itself looked like this, like the blue curve. And in the mixture, it actually was suppressed quite a bit. And we expect that has to do with the interactions of vitamin C with the catechol chitosan film. When these two are in the same solution, the signal is suppressed. When vitamin C is by itself, you can see a larger signal. So in solution, in the mixture, here you have the catechol in the film, and when clozapine comes in, it undergoes redox cycling. It's constantly being oxidized, reduced. The catechol in the film is being discharged. It's being depleted of electrons as this happens. So then when you mix vitamin C in there, vitamin C actually reacts with the catechol to recharge it rather than reacting with the electrode. So that's why the signal is suppressed, and then we don't see this interference because of the selectivity for the film for clozapine, and because of the interactions of vitamin C with the film. So the vitamin C peak suppression may actually contribute to the lack of electrochemical interference from vitamin C. So just to conclude, I showed you what the interference of vitamin C looked like for bare unmodified electrodes. We saw quite a bit of interference. Then with this chitosan catechol film, we were able to amplify clozapine 9 times. And then we were also able to suppress vitamin C. So the performance here for clozapine sensing is much higher, and the interference is decreased. And so just again to reiterate, our motivation is to devise a point-of-care monitoring device to monitor the treatment of clozapine, which needs to be done frequently and in a more convenient manner. And this has the potential for personalizing and also improving mental health care system. In the future, we want to characterize other potential sources of interference in blood, and also we want to incorporate chemometric and signal processing and pattern recognition techniques into our processing part of the device. So I just want to thank everyone for your time, and I'll take any questions now.